Thank you so much. In this presentation, I'm going to explain the work that I've done during my last 5 years of PhD, along with Fernando Fernandez and Ángel García. This is the outline that I'm going to follow during my presentation. The first part is going to be an introduction, and I'm going to tell also a bit of the state of the art. The second part is I'm going to tell the now therapies architecture, which is our first attempt to create a control architecture, a generic control architecture, in which we can replace the use case easily without needing to do so many changes in the code. And then in the third section, I'm going to explain the proposed guidelines that we have developed according to the lessons learned from the previous now therapies architecture. Then in the fourth section, I'm going to explain the MLARAS architecture, that it has been developed following the previously proposed guides of section 3. Then I'm going to explain the opportunities and failures work that I did in the Carnegie Mellon University. It's a joint work with Professor Manuela Veloso. And finally, I'm going to explain the last use case in which we have applied MLARAS completely, which is the logistics league competition of RoboCup. And finally, I will finish with some conclusions. The main motivation of this work is that autonomous robotic is very complex. There are types of sensors, actuators, and to make them behave coherently, deliberation processes are needed. However, deliberation in general is very complex and requires a lot of computational power. But now it's becoming feasible for real systems. Anyway, to coordinate deliberation, sensors, and actuators, an architecture is actually needed. But one part that frequently is not so much commented is that the use cases must be defined by someone. And that person is not usually the engineer, is the end user. So how to really implement them? In this thesis, we have worked in 4 different use cases: the rehabilitation, geriatrics, the butler, and logistics. And the challenge here is to move from the use case of rehabilitation to an actual robot. In this case, our robot is called Now Therapist, and it's useful to rehabilitate children with upper limb impairments. Then the geriatrics use case was transformed into the Clark robot, in which we have developed the deliberation model. Then the joint work that I did with Manuela Veloso in the Carnegie Mellon University was performed with the real cobot robots from there. And we have created a new scheduler taking into account opportunities and failures. And then the last use case is the RoboCup logistics simulation. It's the only one that it's simulated, but because the actual competition is also in simulation. And the peculiarity of this use case is that it's multi-agent. So my thesis is located in the middle of these 2 elements, in particular between the use cases and the actual robots. So we want to know how to implement this use case into actual autonomous systems. So use cases are a very important part of my work, and they can be seen as action plans. For instance, in the butler use case, we could have a robot that needs to make a coffee and bring it to someone. In that case, the robot may need to open the door, then move to get the coffee, actually make the coffee, and then bring that coffee to the person involved. The problem is that the environments are very stochastic and they may invalidate the previously planned plans. So a reasoning strategy is needed in order to replan when something unexpected occurs. There are 3 different main reasoning strategies. The first one is deliberative, in which all modules work with deliberation, like the sense plan act philosophy. They can plan very far in the future, but they are very slow. On the other hand, we have the reactive strategies in which all of them are reactive. They are very fast, but their plan are very short-term. And the most modern strategies are all hybrid. They join the best part of both worlds, deliberative and reactive, like hierarchical architectures. And in particular, layered architectures are the ones that is the one that is developed more in this thesis. So regarding to the control strategies, there are two different ways to approach. In one way, we have the procedural control, which is state machines. They are very difficult to maintain for very complex use cases, but used wisely, they can save a lot of deliberation time by taking out all of the easy parts of the problem. They can be modeled using behavioral trees, and they can be, for complete use cases, can be modeled using these three sets. In the right part of the slide, we can see an example of one of these deliberation trees. This node is the starting node, and it leads to a selector node. Below this node, we have 5 arrows, and one arrow will be selected depending on some preconditions. In this case, only the center arrow has been expanded. That leads to another node, which is a sequential one. And below this node, there are 3 arrows. In a sequential node, this arrow is going to be executed first. It only has one terminal action. So when this action is finished, then the next node can be executed. The next node is the center one, is a parallel one, which instead of only one action, in this case, these have 5 parallel actions. When these parallel actions, all of them have finished, then the next one is executed, that has 3, and so on. The next, on the other hand, we have deliberation, which is very useful to manage complex use cases because we don't have to maintain very complex state machines, but the problems can be very difficult to solve. And because there are search processes involved. So decomposing the problems into simpler ones can speed up the deliberation a lot. In such way, using a layered decomposition can be very useful, in which the higher layers may be more reactive, and the lower layers, which are more in contact with the hardware itself, can be more reactive. PILIA is one of the most important state-of-the-art works in our case. Mm-hmm. It's a planning and execution system focused mainly on classical planning. In fact, it has an automated planning in this module here that it's used as a black box, so it can be replaced at any time. This system uses an ad hoc abstraction translation because actions needs to be translated from a high level to reason with to a low level that the hardware can interpret. And states must be translated from a low level, which are the sensors, to a high level to reason with them. And it can also monitor the execution, replanning when the state is invalid. If we look at the right part of the slide, this one represents that the robot has sent a low state to the executive module. Then this low state must be transformed into a high-level state to reason with, and then this high-level state is sent to monitoring to compare it against the expected state. If these states are not compatible, then the new state is sent to decision support to reason with, and at that moment, the automated planner is going to generate a new plan that is a high-level action plan that is sent to monitoring, and then monitoring is going to return the first action of the first high-level action to executive. Then executive needs to transform this high-level action into a low-level action for the robot to execute it, and that low-level action set then is sent to the hardware. But there are many more examples. In this table we have in the state of the art. Here we have LAS, T-Rex, Rosplan, Cortex. All of them are ordered by in ascending order by year. And if we look at the table, no one fulfills everything that we want. What we don't want are ad hoc mechanisms or maybe customized automated planning. And if we look at the declarative column, we can see that no one has a full use case declarative definition to ease the modifications of it. Only some of them has a multi-layer deliberation, and only the latest ones use generic middlewares. So the problems of these architectures is that there is a lack of guidelines and standards to face the construction or the designing of the new system from the use case. So you start using taking one decision or other without having something clear to guide you. And that makes very difficult to reuse previous works. Also, use cases are hard-coded by developers, but however, they must be the use cases must be defined by the end users. So here we have a very big gap that it's not really completely solved. And there are also hard-coded abstraction conversions, and that difficulty is the maintaining of the systems and also the modifications, not only by developers, but also by the end users. And usually the state-of-the-art uses very complex and slow deliberation models, which are very rich in features, but if you decompose the problem into simpler ones, sometimes you can get rid of this that advanced features and use simpler models which are much faster. And there is a lack also of a multi-layer deliberation support. In general, all of them slow down the development and advancement of autonomous systems. So the main objective of this thesis is to ease the use of standard deliberative techniques in use case oriented cognitive architectures for autonomous systems. This general objective can be subdivided into 6. The first one is to design architectures whose structures reflect the use case by using formalisms to involve the user in the behavior development, and easing the use case modular decomposition into sub-problems by designing layered architectures to organize the knowledge. The second objective is to define relations among the architecture components and layers, and then use state-of-the-art deliberative techniques like automated planning and also MIPs. We want to carry out objectives 1, 2, and 3 declaratively. We want to design also the guidelines that I've said before to apply deliberations in these systems without being blind, and also evaluate all of the previous objectives in real systems. So regarding to the deliberation techniques, automated planner is the most important one of the most important one for us. It relies on a generic planner that finds action plans for certain goals. In this case, we have to define an initial state, and we have also a final state with some of the goals that we want. The automated planner is going to find automatically the plan of actions to transform this initial state into this final state. The automated planner uses a declarative formal language, which is called PDDL, but needs to interleave planning and execution when something unexpected occurs that invalidates the previous plan, using one of the recent strategies that I explained before. And there are also multiple paradigms like classical, probabilistic, temporal, etc. The second technique that we have used is the mixed integer programming, which is a very fast way to reason with numbers and time, and we have used in our scheduling processes. It has also declarative rules and problem. But when the paradigms are more complex, they are also more slower. So that's why we choose the simplest paradigm of automated planner, which is the classical one, because it has the most advanced heuristics for it. Now I'm going to explain the now therapist architecture. That's as I told you in the first part. Is our first generic attempt to or first attempt to create a generic architecture to switch and replace the use case without needing to do so many modifications. I'm going to show you a video. I hope you can see it correctly of now therapist to explain better the use case. Now therapist is intended to perform rehabilitation exercises for children. As we can see here, we have a robot in front of a child, and in the left part of the screen, we have a 3D sensor. The objective of the robot is to perform poses that the children need to imitate. If the children performs the pose correctly, then the next pose is executed without problems. But if the child is wrong with his pose, then the robot can say, hey, I'm seeing that this arm is not correctly well, please correct it. Or the robot can even copy the posture of the patient by saying, hey, I'm seeing that your arms are in this position. You have to move your arms from this position to this other position. All of this has been achieved with using automated planning. But this use case was designed using the therapeutic protocol of the Hospital Virgen del Rocío de Sevilla, in which the physician diagnoses the patient, and then he determines a certain therapeutic objectives for him. Then the step A and step B are the two steps that have been solved with now therapist. In step B, the task is to define the whole therapy for that specific patient. A therapy is composed by sessions, and each session is composed by several exercises. These three elements are those that are managed with in the step A of now therapist. And each exercise also comprises a predefined number of poses, which are out of this step because they are predefined. Step B, on the other hand, is how to execute each one of the sessions that has been previously planned in step B. And this execution is performed using with the robot and also with the child in front in an online fashion. So these are the layer decomposition that we perform for now therapist. We have 3 levels. In the high level, we plan all of the therapy sessions. We use classical planning, and we are taking into account many complex constraints like variability constraints and also all of the therapeutic objectives that were prescribed by the physician. And it's performed in an offline, it's performed offline prior to the actual session execution. And the daily plannings are triggered manually by the physician. The medium level is in charge to plan the actual execution of each session. It uses also classical planning and PILIA to replan online. And its problems are converted from the high level. So the sessions of the high level are going to be the problems of the medium level, which involves action like say hello, say goodbye, execute exercise 1, correct the pose, etc. And we have also centralized all of the ad hoc abstractions and many other mechanisms into one module called the executive. The low level needs to play, it's transparent for us, and it's to plan each movement of the robot and the position interpolation from one pose to another, and also the sensor. This is an example of the high level, which is the therapy designer. In this table, we can see that each row belongs to a session, and each column, it's the order of the exercises. As we can see, all of the sessions are different because of the variability restrictions, and all of the exercises are suitable for the therapeutic objectives prescribed for a specific patient by the physician. In this other slide, we have the medium and low levels of the architecture. In the left part, we have the robot and the Kinect sensor that we used. They can be replaced at any time without so many modifications. So we consider that our architecture is also independent from the hardware and from this hardware. But all of the sensor data and the perception is sent to the executive model, and this executive model generalize this data into a high level state of the world to reason with. Then this state of the world, Pelia reasons with these states of the world, and then it sends plans of action to executive, medium level actions. And each medium level actions is then decomposed into low level instructions. In the bottom part of the slide, we can see the catalogs of medium level actions of low level instructions of now. Regarding to the technical evaluations, I've shown here two results. The first for the planning times. In this plot here, we can see the remaining planned actions. As for more remaining planned actions, when longer is the plan, in theory, the time should be higher. And in the y-axis, we have the time. These crosses are replanned actions, and this line of process below are the previously planned actions. So as we can see here, the difference between them is not too much, and the growing in planning time is almost linear. So that is very suitable for a social robotic use case like now therapist. On the other hand, we have also the generalization results. Apart from the mirror use case that I showed in the video, we have developed also the Simon game. And in other works, 4 more use cases have been developed, like the reverse Simon, the Simon Says, dancing, and also teaching movements to the robot. In total, 6 different use cases were developed using the now therapist architecture without too many faults. But the most important evaluations that we have done with our system were the field tests with the with patients, with actual patients. There were three children. The first one was with 3 children during 1 session. The second one was with 8 children during 4 months in a weekly basis. And then the third one was with 10 children during 15 days in a daily basis. In overall, we have performed tests with 244 children, healthy and patients, and 429 sessions. And in general, all of the interactive outcomes were very good. But there is another thesis of José Carlos Pulido, which involved the clinical and human-robot interaction analysis completely. So the lessons that we have learned from now therapies is that multi-layer deliberation works very well, because simplifying the problems the way we did speeded up the deliberation a lot. But we found that guidelines were very important, because we have taken so many decisions without having someone to tell us how to proceed with our specific use case. So we find that guidelines are very important. We also need to fix the monolithic executive model because it is very hard to maintain, and small changes are very hard to apply. For instance, if our therapist wanted to change, for instance, a wording of one speech, he needed an engineer to do that. But aside of that, there are some features that are needed for now therapists too, like a full declarative configuration to ease the changes, action interruption, and online high-level planning. Because only with the 4 use cases that we have developed in this thesis, only the first one could be developed with the current architecture. Nor the geriatrics, the butler, or the logistics could be developed with it. So in conclusion, the now therapist architecture wasn't enough for these new use cases. This is the first half of my presentation. Now I'm going to explain the proposed guidelines that we developed, taking into account all of the lessons learned from now therapists to, and the main objective of these guidelines is how to face the system design from the use case. Below, you can see how are the summary table of this of this system, but don't worry, it's very slow. It's not intended to be read. I'm going to explain it in the next slides. But going again to the 3 points in the top part of the slide, we have 3 different design processes. The first one is to design the deliberation strategy, which is the problem decomposition of for the specific deliberation strategy, deliberation mechanism that we have choose. The second one is the planning model, in which we have to define and how to model the domain and the problem. And then the third one is how is to design the executive model about how to interleave the planning and execution. Regarding to the first design process, that is the deliberation strategy, we have to design the planning paradigm, if it's going to be classical, temporal, probabilistic, etc. Well, we have also to define the on-layer reasoning, if it's going to be deliberative or a reactor. If it's deliberative, we have to determine how to decompose the problem into different layers. This is better explained with an example or with now therapists. If you remember, now therapists had a high level of planning and a medium level of planning. In this structure, we could imagine that this could be the whole therapy that has to be planned in the higher level, and each action will be each one of the sessions that then are going to be planned in the medium level. So this will be the medium level plan for each one of the sessions of now therapist. We have also to determine how far we want to go with deliberation. This is the planning horizon. We have another example of now therapies, which involves only its high level. To develop the high level, we decided to use a divide and conquer strategy to speed up the process. In this case, the high level, instead of having only one deliberation process for all of the sessions, for all of the therapy sessions, firstly, we plan the first session, and then we translate the plan, parts of the plan, to the problem of the second session, and we plan the second session, and so on. These mechanisms, with these mechanisms, we can speed up the deliberation process a lot without losing too much quality in this specific case. And the last part is the model partition. This is explained also with the 6 now therapist use cases. Imagine that we had a high level that instead of only preparing mirror sessions could also model and plan sessions with the 6 different games. In such high level, we could have the first action that, for instance, could be the mirror game. The second action could belong to the mirror game. So this will be a deliberation process in which the domain will be only the mirror. And in this case, this will be, for instance, the Simon, and another one for Simon. This will be the domain for the Simon. So instead of having the 2 games together, we can separate it in different domains. That is useful also to ease the deliberation. Regarding now to the second designing step, with the planning model, we have to define the actions and the states that we are going to use. For the actions, we have to determine a prediction which we call the nominal behavior. The nominal behavior is an assumption and in some sort of a prediction too, which is the shortest plan that can lead to the goals that we want. But of course, environments are dynamic, so unexpected events can occur. So we need also to define corrective actions that can solve the problem, the unexpected problem, and return to the nominal behavior as soon as possible to achieve the goals that we need. We also need to define the state and how the predicates and the features of each one of the predicates that need to be. All of the details are in the dissertation document. In the third designing process, we have the executive model which involves the interleaving of planning and execution. So we have to determine the scheme of the continuous monitoring, and also the online knowledge management, which involves the high to low decompositions, because we need to transform high-level actions into low-level instructions or actions for lower layers. And also we need to transform states from low-level states of the lower layers to something higher, on a higher level of abstraction, to reason with our deliberative techniques. And we have also to face some deployment issues depending on the deliberation technique that we have chosen. Now I'm going to explain the MLARAS architecture that has been designed and developed using the proposed guidelines that I explained in section 3. MLARAS stands for Multi-Layered Architecture for Autonomous Systems. It is focused mainly on classical automated planning, and it could be considered as a PILIA generalization that uses temporal aspects with condition annotations, stochastic aspects with the monitoring and the replanning, and also hierarchical aspects in its very structure of layers. And it also uses explicit abstraction conversions between states and actions, and it has a complete and full declarative use case definition, so that all of the use cases can be defined in MLARAS without needing to program a single comma in a imperative language. This is a zoom in of one of the layers that we have seen in the previous figure. The first, these are the modules of each of the layers. The first thing that is going to happen is that a high-level action reaches the executive module. This high-level action must be transformed into a set of goals to deliver with. Then the next action that is going to happen, well, the next thing that is going to happen is that it's going to receive a low-level state at some time. This low-level state must be transformed into a medium-level and a high-level state. A high-level state is going to be transmitted to the higher layer of reasoning, and the medium-level state and the goals are going to be sent to monitoring to monitor the execution, and also perform search processes when needed. The search processes are going to send medium-level plans to monitoring, and then the next medium-level actions is sent to executive in a similar way of PILIA. This medium-level action must be also refined into low-level actions so that they can be interpreted by the hardware or a lower layer. Aside from these modules, we have also several declarative files which are used to model the knowledge. The domain and the problem template depend on the deliberative technique. In the case of automated planning, they are written in PDDL, but the action, the compositions, the durative conditions, and the state generalizations and goal relations have been developed in this thesis. And one important aspect of this work is how to manage temporal aspects, because actions have duration, but this duration sometimes is not known. For instance, if we expect that the patient is going to put the correct pose in front of the robot in a certain moment of time, we are going to be very wrong. So interruption of actions in the middle of their execution is very important. Imagine that we have a robot with a speech that lasts for about 20 seconds, and the person leaves the area in the middle of the speech. If we don't interrupt the action, the robot is going to continue speaking alone. So that's very absurd, and we should solve that. For it, we have developed the overall and finish when annotations that work similarly to temporal planning without overlapping actions. And they are controlled by MLARAs, not by the planner. That's very good because we can save a lot of deliberation time by simplifying the deliberation model. Now I'm going to explain the joint work with Professor Manuela Veloso in the Carnegie Mellon University with the cobots using the butler use case that I told you in the first part. This robot is the same as the other that has to bring a coffee to a person. So firstly, this robot is going to go to get the coffee, make the coffee and prepare it. And since in the moment that the coffee is prepared, it has a cooling down time. So if it lasts too much time to bring it to the person, the coffee is going to get cold. Also, many things can happen in this process, like for instance, that the person is in the middle of the corridor. In that moment, the robot can give the coffee to the person, and if the robot doesn't takes the chance to do that, the robot is going to continue its path to his office, and it is going to try to deliver it, and the person is not going to be there. So that's a failure. The previous one was an opportunity, and this is a failure. Of course, much more complex things can occur. For instance, if we have a very important person in the middle of the corridor, in this case, the robot has many different options, like for instance, attending the VIP before bringing the coffee, at the risk of bringing it cold, maybe redoing one of the actions or cancel one of them. We have solved these things by creating a new monitoring model for the cobots, in which we have the task pool with tasks that are sent by the users directly to the robot. And we have annotated the possible opportunities and failures using a declarative language, and some other aspects like the priority of each task and the cooldown time if needed. So our rescheduling of our system can add or remove tasks in the pool without needed to be directly inserted by a user. And it can also interrupt the current subtask if the new schedule is better than the previous. The new scheduler, by the way, is based in MIPs. And I'm going to show you an example of the use case, our fastest example of the robot. This is in Pittsburgh. This is one of the cobot robots, and this is the interface that I developed to perform all of the experiments. In this case, I'm going to schedule a very simple task with only to bring a beverage to someone, and then it's going to plan and to serve the bottle of water. The robot starts moving, and it knows where it has to get the bottle of water, which is in this door. Then the robot doesn't have grippers, so it waits for someone to put the bottle in its basket, and then the robot continues to bring the bottle to the owner of the task. So regarding to the experiments of this part, I'm going to show you the cobots, the solving time plot, in a similar way of the other that I show you. This is the task pool size. When we have more tasks in the task pool, the average solving time is higher. And in the y-axis, we have the average solving time for all of the tasks. So we have performed 3 experiments here. One for 13 seconds, waiting for an optimal solution. Another one with 10 seconds, also waiting for an optimal. And 10 seconds at maximum, but storing a suboptimal enough solution. And we found that the quality in 10 seconds suboptimal is acceptable for the cobot use case. MLARAS implements this work in, and we can see it in this sequence diagram, in which the lower layer sends the low-level state to executive. This state then is transformed into a medium-level state to reason with, and monitoring determines that these states are compatible. However, instead of stopping there, monitoring determines that there could be an opportunity or failure there. So a new deliberation process is then executed while the robot is currently executing their tasks. And if the new plan is better than the previous one, then the action is replaced and the previous task is cancelled if that's the case. Finally, I'm going to explain the logistic league, which is an instantiation of the MLARAS architecture in the RoboCup logistics simulation. The goal of this competition is to build as many products as possible for score. And if a product has more rings, then it is going to be more valuable. There are two teams of 3 robots working at the same time. And each team of robots should cooperate with their team members in order to be faster and earn more points. There are also several stations scattered through the playfield intended to mount the bases, the rings, the cup, and deliver the product to. So the things that we have done, the parts that we have replaced is the deliberation and the abstraction conversions, which means that MLARAS was applied in this use case in its full glory. And we have also created a new PDDL domain, which is based on classical planning, but it has the peculiarity that it has a centralized plan for the 3 robots. And that means that this is a multi-agent use case, but solved with classical planning. In this case, we have used a generic partial order plan interpreter. This is an example of an output plan. This one that precedes the 3 first actions means that these 3 actions are going to be executed in parallel because they belong to 3 different agents. Then these 2 actions are going to be executed in parallel, and when they have finished the 2 next, and so on. And we have also designed the opportunities management by rescheduling when new orders are sent by the referee. This is the overview of MLARAS applied to the logistics use case. In the top part, we have the referee, which is sending the orders, and they are being decomposed iteratively until it reaches the lower layer, which is the robots. And then the low-level states are gathered from the robots, and it reaches the monitoring part on the top part. In this case, level 2 is the order schedule that because we have several orders sent by the referee, and we have to select which ones we want to build because we only have 15 minutes of limit. Then level 1 is the robot actions that needs to be performed in order to actually build the products. So go to one station, put a cap or a ring or things like that. And then level 0 is transparent for us also. And it's the way each robot needs to move from one part or another, or maybe move each gripper. Aside of these elements, we have also defined all of the declarative files. Right, we have the domain written in PDDL and the problem template too. And we have also the durative conditions files. In this case, we have the medium level action enter, for instance, and the finish when conditions. Finish when determines when an action has been finished. There are some technical aspects here, and we have here, for instance, that the agent must be ready. That's what the 3 means, in order to consider it finished, the action again. The action decompositions files, we have here, if we look at the bottom part, two high-level actions that share the same low-level action decomposition. In this case, this decomposition has two sets of parallel low-level actions. The first set only has one action, and the second set has three different actions that that have to be executed in parallel. Then the state generalizations file, in which we have conditions that determine that depending on the things that happen in the state, then it will delete or add things in the model, which in this case is the PDDL. And we have also the goal relation files that means that when this level receives a high level action, which is execute order with all of these parameters, then the goals like product piece, the cap of this product piece, etc., must be added to the PDDL goals. The results of this system is that we have a planning time of 10 seconds, which is enough. The three agents can execute orders in parallel in spite of using a classical planning approach. And the scores that we have obtained are over 170 points if there are no obstructions from other robots. And to compare, the last winner of the competition has an average of 139 points, and the second one only 32 points on average. And all of these have been done using only declarative files, the declarative files that I explained to you before. So in a nutshell, we could say that Now Therapist was a success as a real project, and that MLARAS eases the development of autonomous systems. For instance, if we were to recreate Now Therapist using MLARAS, that would be very easy. And MLARAS achieves all our thesis objectives with evaluations of certain parts in 3 real robots and one simulated environment. And regarding to our contributions, the first is that we have developed guidelines for deliberation in robotics, focused specifically on automated planning. We have implemented a layered deliberation system, which has been fully instantiated in a multi-agent logistics environment. We have widened the mechanisms to apply classical planning in real world scenarios by taking into account temporal preconditions and also interlayer interruptions like opportunities and failures. And we have developed declarative language to ease the use case refining even for the end user. And especially the high to low file, which models the behavioral trees that I explained in the first part of the presentation. There are many future works here, of course. For instance, a deeper study of the any plan time refining, a graphical tool to generate the declarative files, or even using a plan reuse mechanism to save deliberation time and even avoiding it completely if we can learn from previous plans. And we can also study different use cases to like improving the multi-agent support and also explore the limits of the layered deliberation of MLARAS. All of this work has been published in 17 different publications since 2014. 4 of them are JCR journal articles. And aside of the scientific world, we have won several accolades with our Now Therapist project, and we have raised a good amount of money to consolidate a new spin-off, hopefully in the next month. So I think that that's all by my side. So thank you a lot for your attention. And if you have any questions, I will be pleased to answer you. Muchas gracias.